Hi guys, welcome to my channel. Today we're going to talk about groups of order 4. In particular we're going to classify them and we're going to see that there are 2 of them up to isomorphism. So, to be more precise, I'm going to show the proposition that there are 2 groups of order 4 up to isomorphism. And our strategy is going to be that first we're going to recall the concepts of this proposition. And then we're going to construct 2 non-isomorphic groups of order 4. And then we're going to end by showing that there are no others. So this last step is going to be the most involved step. And this is where we want to show that given any group of order 4, that group is going to be isomorphic to one of the 2 groups constructed in step 2. Okay, so let's get right into it. So here is a quick reminder of the necessary concept. So the order of a group G is just the number of elements in G. And an isomorphism between 2 groups G and G prime, that is a function f from G to G prime, which is bijective. So it is bijective and a homomorphism. So let me recall here, bijective means that for all x prime in G prime, there is a unique x in G such that fx is x prime. And homomorphism over here means that for all xy in G, you want to say that the function f preserves the group structure. So we say that f, and then here we have multiplication in G over here, and that is the same as first applying f to x, and then applying f to y, and multiplying now in G prime. So this formula is usually just written as f xy is fx fy, where you just suppress this notation of the multiplication, as you do most usually when you are working with groups. And finally, we need the order of an element. We're going to use that concept in the proof of our statement. So the order of an element x in G is going to be the smallest number. So the order of an element x, this is the smallest number, d in n bigger than 0, such that x to the d is 1, is the e. So it's the first time that if you take x and then x squared and then x to the third, you might at some point end up with the neutral element e. And the d is the first time that this happens, because it might be that if x to the fourth is e, then maybe x to the 2 is already also e. Okay, so here is the first group that we're going to construct of order 4. We're going to call it G, and I've drawn here 3 squares, and I'm going to use them to give the elements of my group. So first, consider a rotation of this square by 180 degrees. And if we write it down in symmetric group notation, this rotation maps this point 1. This point 1 goes first to 2 and then to 3. So in the whole rotation it maps 1 to 3. So we can write down 1, 3. And similarly this point 2 goes to 3, 4. So we have 2, 4. So this notation is just when we consider our elements as elements of S4. So remember, S4 was the group of bijections on 4 elements, and this rotation of my square gives a bijection on the 4 corners. So I'm going to represent this rotation just by what it does on the corners, like so. Similarly, I can reflect my square in this axis, and then I see that 1 goes to 2 over here, and 4 over here goes to 3 over here. So we have our element different color. 1, 2, 3, 4. And now the last one, I take this one, and then I map 1 to 4 and 2 to 3. Okay. So let me move this down a bit. So I let now the group G be, I always need the identity element. So let's give these elements a name. I can give this the name R, and let's call this guy S, and let's call this guy T. Then my group is going to be E, R, S, T. So now we need to check. This is a group. So since these are elements of S4, all we need to show is that G is closed under multiplication. So in other words, if you know what it means, we need to show that G is a subgroup of S4. So it suffices to show G closed. So G is closed under multiplication. So there are 2 ways to do that. Either you can take these elements and multiply them all together pairwise and see that it gives another element in your group G, and that's a lot of work. But you can also look at the picture and you can observe that if you do a reflection and another reflection like this, then you get this rotation, and if you do this reflection and this rotation, then you get that reflection, and etc. So if you look at the picture, you almost immediately see that this is closed under composition, so G is in particular a group. Okay, so let's move on to the second group. As you see, there's not much space for the second group. But that's okay, because it's going to be very quick to introduce the second group, because you've probably already seen it. Namely, we take the cyclic group C4 on 4 elements. And recall that another way to write this is Z mod 4 with addition. And another way is the group E rho squared rho to the third, where we have that rho is a rotation now by 90 degrees of this square. So this is my rho. Now obviously if you do rho 4 times, then you are back where you are, and so this is also represented by row is 1, 2, 3, 4 in S4. And then row squared is also can be thought of as an element in S4. So these are multiple ways of thinking about the same thing. From here on we're going to just call it the cyclic group of 4 elements, and we're gonna take a row as our generating element of C4. In other words, every element in C4 is a power of row, like here. Okay, so here comes the bulk of our argument, namely now we let H be any group of order 4, and we want to show that H is isomorphic to either our group G as constructed here or to our cyclic group of order 4. And so there are 2 cases, and you can think about which cases there are. If you want to think about it more, you have to pause the video now, because I'm going to tell you. The first case is that H is cyclic. That's the easy case, so let's get it out of the way. So if H is cyclic, then H is C4, because 2 cyclic groups which have the same order are always isomorphic. To see that in this case, take a generator, say X in H, so recall that it means that H is then E x squared x to the third. And now if we compare this notation to this notation, it's pretty clear how we can get an isomorphism, namely then take the isomorphism from H to C4, which maps x to row, and in general x to the n for any n, to row to the n for any n. So that's my isomorphism. And if you don't see why this is an isomorphism, it's a good exercise to write down, and it shouldn't be too hard. And now, so this was our first case. Now we go to our second case. So because we've now dealt with the case that H is cyclic, so now we suppose that H is not cyclic. And then we're going to use a little result, namely we're going to use that the order of an element in a finite group always divides the order of a group. And you've probably heard this result. If not, you might have heard of Lagrange theorem. So let me write something down. So let X in H just be any element. Then the order of X divides the order of H, which we can write like this. Or let's write it like this. The order of H. And this follows from Lagrange. So at this point I don't want to go into Lagrange or why this is the case. We're just gonna assume it and work with it, but it's fairly standard. Okay. So let's use this now. We know that H is not cyclic and that H has order 4. So that means every X in H has order 1 or 2. Because if we have an element X in H of order 4, then H must be cyclic. And we know that the only element in H which has order 1 is the identity element. So we have that every x in H which is not the identity element has order 2. Okay, so now we're going to write down H as E, X, Y, Z. And the funny thing is that now we can already write down our isomorphism. So we can write down very explicitly an isomorphism F from H to our group G. We call this was E with this rotation and these two reflections, which we called S and T. So let me remind you over here. This was R, this was S, and this was T. Okay. And we map E to E, obviously. And let's write X, Y, Z. And they go to R, S, T. And the funny thing is, I don't really remember which order I prepared. And as you will see in the proof, it doesn't really matter. I can take any order here. I can map X to S and Y to R, for example. Okay, so we write down F, and we need to check. So obviously F is a bijection, and we need to check F is a homomorphism. So look, these elements have all order 2. And because this guy is a rotation by 180 degrees and these are both reflections, they also both have order 2. So that means that F, so Fx squared is Fe is Fr squared. And same for y squared and z squared. So it remains to show that the following two facts. One, multiplying any two elements of x, y, z, so any two distinct elements, gives the third. So for example, x times y needs to be z. And 2 is check the same for g. Okay, so let's show one. And here I want to remark that if you know about multiplication tables, then this argument follows directly from making the multiplication table for H. But it boils down to the following observation. Consider the function so this is not a homomorphism, but it's a function phi from H to H, which maps any, say, alpha to x alpha. So we multiply every element by x from the left. And then we remark that phi is a bijection. Indeed, it has inverse the map that maps beta to x inverse beta. Okay, so we have now a bijection from H to H, right? And we know that it maps E to X. And we know that it maps X to X squared, which is E. And then we have Y, Z left. And either it maps Y to Y and Z to Z, or it flips them. So suppose that it maps Y to Y. So suppose phi Y is Y. Then xy is y. But then we can cancel y on the right side. We can write x as x, y, y inverse, which is then y, y inverse, which is E. But x was not the identity element. So phi y must be z. And because we had a bijection, we know that z must then be y. So from this argument it follows that xy is z and xz is y. And the same argument works for y and z. Okay, so we've checked number 1, that multiplying any two distinct elements of x, y, z gives the third. Now we need to check the same for g, but here we only need to remark that g is also a group of order 4, where every element which is not the identity has order 2. So I can just repeat this whole argument for g, and then we get the same. Okay, so this is already done. Okay, so now we're actually done, because we have this function f from a to g, which is a bijection, and we need to show that it's a homomorphism. And because every element which is a non-trivial has order 2, the multiplication over here is respected, and multiplication between these different elements is respected, because we have that that for example fxy is fz, right? And fz is ft, st, and t is rs, and rs is fx, fy. So, and same for other elements. So f is a homomorphism. Okay, so this is what I wanted to say. I think we've shown now that that any group of order 4 is isomorphic to either the cyclic group or to this group of these chosen symmetries of the square. So there are two groups of order 4 of the isomorphism. I guess I didn't really say why these two groups that we created are non-isomorphic, but after the fact it's, I think, clear why they are not isomorphic to each other, because the cyclic group of order 4 has an element of order 4, namely the generator, and this group G has no element of order 4, so it cannot be cyclic. Okay, that's all for today. Thank you so much for watching, and see you next time.